I can't believe I forgot to do the stream. It takes 1 minute.
Yeah.
You know that we can just do it live without the customization stuff that we usually do. We are live. No?
3:10, no, 3:05, 3 p.m. Create stream. Sorry, everyone. Copy.
So,
are you streaming already? It looks like we're streaming.
It looks like, yes.
Okay. I don't know how that happened.
And you can see my screen?
Yes, we can.
Okay.
Let me just see if we are live. That's weird. Let me just see. Yes, we are live. Looks like we are live. Okay.
Okay.
We apologize for this. Sorry about that.
No problem.
Okay, so hi everyone. Today is the Quantum Day, and it's a pleasure for us to have Adriana Moreo in a Quantum Matter seminars to talk about her work of orbital selectivity in low-dimensional systems using the merge calculations. Thank you very much, Adriana, for being with us today. So the stage is all yours.
Thank you, Crisia. So I want to thank both Crisia and Adrian for inviting me and giving me the opportunity of sharing my work with all of you. Today I'm going to talk about orbital selective correlations and block magnetism in low-dimensional iron-based superconductors. This is work that I did with many collaborators. The main person is Jason Herbrich. He was our postdoc at University of Tennessee, and he's now a professor at Wrocław University in Poland. Other key collaborators are Nitin Kaushal, Nirav Patel, Maria Daghofer, Alberto Nochera, Gonzalo Alvarez, and Elvio Dagotto. So I'm going to start with a brief overview of the high TC superconductors. So these are materials characterized by iron and in particular the iron-based high TC superconductors. Okay, so these materials have planes of iron together with okay, I think okay, so these materials have planes of iron together with, could you excuse me for a second, because I think I may not have the right talk here. I'm seeing something that, so let me just make sure I have the version that I'm supposed to have. No, okay, sorry about this. Sorry about this, I need to stop the share. Okay, sorry about that. I was with the with the wrong talk. Okay, so can you see the talk?
Yes.
Okay, so I'm going to go with a brief overview of the iron-based superconductors. So these are materials that have planes of iron with a pnictide either above or below the planes. The irons form a square lattice, and at the center of the plaquettes, either above or below, we have a pnictide. Okay, so these are the planes. And these materials, when they are undoped, have magnetic order. The magnetic order that they have is of the form pi0. Okay, so antiferro in this direction, ferromagnetic in this other direction. They are bad metals, so this is something different compared with the cuprates that are mode insulators. But like the cuprators, the cuprates with doping, they become superconductors. In addition, they have a very complex Fermi surface. At the center of the Brillouin zone, there are hole pockets. At the boundaries, there are electron pockets. These pockets nest with each other with momentum pi0 and 0 pi. And the orbitals that contribute to the bands that form the Fermi surface are basically the 5d orbitals, although majorly the T2g orbitals, dxz, dyz, and dxy. Because of the nesting of the Fermi surfaces that at pi0 and 0 pi momentum, early on people thought that these materials could be explained in the weak coupling regime, and also particularly because the ground state was a metal. So that was the assumption, but basically at the same time, other people started studying the problem starting from the strong coupling regime. Okay, although it wasn't very exact, they assumed that the spins were localized, and then looking at the structure of the lattice, they found that, for example, these are the irons, okay? And in order to hope to nearest neighbors from iron to iron, one has to go through the p orbital of the pnictide. Okay, so it was basically an overlap like that. And to go to the next nearest neighbor is also through the pnictide. So the resulting effective spin model had J prime and J of the same order. And because of that, it leads to a ground state with momentum pi0 in the magnetic order. However, later on, it was found out that neither of the extremes was a good place to start, and that actually the intermediate values of U over W were the most relevant. In particular, against the weak coupling picture was the fact that there are some materials that do not have the oxygen, the hole pockets at the center of the Brillouin zone, so there is no nesting, but still this kind of magnetic order is observed. In addition to the pnictides, there are other families of iron-based superconductors, like the chalcogenides, in which at the center of the plaquettes of iron, there is a chalcogen such as selenium or tellurium. And these families are also very, very important. So before moving on, let me rapidly make a comparison between cuprates and pnictides. So both materials have planes, copper oxygen versus iron pnictide or iron chalcogenide. Both materials are magnetically ordered in the undoped case, but the cuprates have this checkerboard magnetic order, and they are mode insulators. The pnictides are bad metals, and they have this pi0 magnetic order, and the reason is the hoppings. In the cuprates, the nearest neighbor hoppings are stronger than the diagonal hoppings because of the presence of the coppers in the links, while in the pnictides, as I already explained, both J2 and J1 are comparable. And the other important difference is the Fermi surface. A very simple Fermi surface for the cuprates is just one single band of mostly dx squared y minus y squared character, which is why single orbital models are usually used to study the cuprates. However, this complex Fermi surface with multi-orbital bands indicate that a single orbital model is not sufficient in order to study the iron pnictides. So the models that we need to use are multi-orbital Hubbard models. So the multi-orbital Hubbard models that we are going to use have a tight binding term with includes many orbitals. The ideal number would be 5, but we can use as little as 2. Less than 2 is no longer useful, okay? And we are going to talk about many of those different situations. So the energy scale W is is obtained from angular resolved photoemission experiments or from DFT calculations. While the hoppings and the terms that appear are obtained from the geometry of the lattice and the orbitals using like a Slater-Koster calculation, for example. Then comes the interaction terms, okay, where we have a Hubbard repulsion with many orbitals, and the terms come from the 1/r Coulombic matrix elements that were obtained by Kanamori in the 50s, okay? So the main interactions are the Coulomb repulsion, on-site Coulomb repulsion, that suppresses the W occupancy of electrons in the same orbital in the same site. And then there is this Hund coupling that favors the alignment of the spins of 2 electrons in the same site, but in different orbitals. And the competition between these two tendencies is what is going to unlock the very rich phase diagram of this Hamiltonian. So the next question is, how will we study this Hamiltonian? So the most accurate technique would be Lanczos. The problem with Lanczos is that we can work in very small clusters. So an approach that will allow us to work in larger clusters is DMRG, density matrix renormalization group. The problem with the approach is excellent, but it works very well in one dimension or in quasi one-dimensional geometries. So the question is whether we can go from the plane geometry to something simpler in order to study these multi-orbital models. So the issue is that nature helps us because there are iron-based ladders, okay? So barium iron sulfur is a material that actually contains ladders of iron. So it has a 1D geometry. It's an insulator at ambient pressure, but it becomes superconductor with a TC of 24 Kelvin at 10 gigapascals. So here you can see how it's an insulator. This is the resistivity, but under pressure, the resistivity goes down, and eventually we end up with a superconductor. In addition, at ambient pressure, the material is magnetically ordered. There is an L temperature of 120 Kelvin, and the order that it develops is this structure pi0, antiferro along this direction, ferromagnetic along the rungs, okay? There are more materials with ladder structures. For example, this has the same structure, but replacing sulfur by selenium, we have barium, iron, selenium that also become superconductor under pressure. And at ambient pressure, it has this block-like magnetic structure, okay? Which is, so these are ferromagnetic blocks coupled antiferromagnetically to each other. And there are several other ladder materials, okay? So from the point of view of nature, we can study multi-orbital Hubbard models in ladders, okay? The next question is how many orbitals we will have to consider, because we need to reduce the number of degrees of freedom as much as we can. So in the actual parent compounds, the orbitals that matter are the 5d orbitals of iron. So iron has this electronic structure, but in the parent compound, we have iron 2+, which means that the s electrons do not participate. So we have 5d orbitals with 6 electrons. Studying 5 orbital is very difficult, so an important simplification that is routinely done is going from the 5 to the 3 orbital model, because as I explained, the T2G orbitals are the prevalent ones at the Fermi surface. So the way in which we do this transformation is this orbital is removed, this orbital is supposed to be very high in energy, so we are left with 3 orbitals with 4 electrons, okay? So this is what corresponds to the parent compound in the 3 orbital picture. So now—
Very sorry, Adriana, can I ask you? Here, iron usually is in tetrahedra, and tetrahedra is usually doublet and triplet is higher. So it should be, you consider case when iron is octahedra? So triplet is lower?
Well, no, we are not looking at the geometry. We are working with the geometry of a ladder or a chain, actually. But what we are doing is we are looking at the orbitals that are more prevalent at the Fermi surface. And
but once again, in this ladder compound, this iron is in octahedra or in tetrahedra?
In the okay, let me see.
Because in usual iron-based superconductors, it's always iron and tetrahedra. Arsenicum and selenite, telluride is always iron tetrahedra. But then it's doublet and triplet is above. And triplet will be completely filled. A doublet will be 3 electrons in doublet generate orbitals.
Okay. Yeah, this is the structure, and to be honest, I mean, you will see that we are going to do many more kind of phenomenological things. So we are not really looking, and sometimes, I mean, I was trying to do kind of a hand-waving argument to explain why we are considering this, but there are some times where even you can get some effective orbitals that are not even these DXC, DYC, and DXY. So I'm not going into the details, but probably they will come out during the talk. But at some points, we are using some tie-binding terms that come from first principles, where actually you end up with a linear combination of orbitals. This is basically just to convince you that going from that putting 4 electrons in 3 orbitals is a reasonable way to look at the parent compounds. So
as a model is fine, but the question is whether it's really applicable directly to this.
And I would argue, Daniel, that in order to decide that, we are going to be comparing with experiments, and if we find things that if we find that we are reproducing the experiments, we would say that we are capturing at least some of the most basic degrees of freedom, and if not, we have to go back and refine. Okay, so that will be the spirit. Okay.
Very good. Fine. Go ahead.
Okay, so now I'm even going to try to simplify even more. Okay, so I thought that we were going to work with ladders, and we are go into that. I mean, that is the physics that we are going to have in mind. But in order to go to larger systems, we are also going to look into chains, okay? And the idea is we are going to look into chains compared with the results that we get on ladders. And again, if we get similar results, we are going to work even more with the chains because we can make more progress. To give you an idea, notice that working in a chain with two orbitals is equivalent to working in a ladder with single orbitals, okay, regarding the numerical effort. And for people that want to see whether there is something real about the chains, all I can say is that there are some materials that iron-based materials that actually have iron chains. This thallium iron selenide is one of the examples. The only thing is that the material hasn't been very much studied, and the experimentalists tell me that it's because it's very poisonous. So we don't know if it goes superconductor or things like that, but I would say that from the results I'm going to show you, many of them that happen in chains, maybe experimentalists could become interested about going back to this material. So the issues that I'm going to address are what happens with the magnetic order when many orbitals are active, as in iron chains and ladders. And we are going to find that novel orders in quantum matter emerge. And we are going to see whether, as it happens in the cuprate ladders, whether when we have a multi-orbital model in a ladder, as in the pnictides, pairing occurs. And we are going to see that at intermediate values of U, there are pairing tendencies. So let's focus on the first question, and in order to do that, let me show you the phase diagram that, using a variety of numerical techniques, we obtain for a multi-orbital Hubbard model. So here is the Hund coupling, here is the interaction U. So at low values of U, we found that the system is metallic with all the orbitals participating in the Fermi surface. At large U, compared with the bandwidth, the system becomes a Mott insulator with gap in all the orbitals. But at intermediate values of U, with relatively large values of the Hund coupling, we found this interesting orbital selective Mott phase, in which one of the orbitals becomes a Mott insulator, but the system remains metallic in all the other orbitals. So most of my talk is going to focus on the properties of this phase. So from the experimental point of view, I already told you about this material, barium iron selenide, that has the iron ladders, okay, and that has this structure with the ferromagnetic blocks ordered antiferromagnetically. These are neutron scattering results obtained by Murigal in 2015. Interestingly, these are results that our group calculated in 2014. Here we studied the 3-orbital model with 4 electrons. Notice that the dispersion that we choose, this is in 1D, by the way, the dispersion that we choose is that 2 of the orbitals form a hole pockets at the center of the Brillouin zone, and the 3rd orbital produces electron pockets at the boundary of the Brillouin zone to capture the behavior observed in the higher dimension pnictides, okay? And what we studied was the population of each of the orbitals, and these orbitals are not hybridized, okay? So each one is an orbital. What we found is that at a small u, all the orbitals are metallic, but as we come to U close to the bandwidth, we found that the green orbital becomes half occupied, okay? While the other 2 have a filling of 1.5, more or less. So we can think that if that happens, we may be in the orbital selective Mott phase, so in which one orbital develops this gap, while the others remain metallic. We calculated the density of states with DMRG, and this is exactly what happens, okay? So the green orbital develops a gap, while the blue and red orbitals remain metallic, albeit they develop a pseudo gap at the chemical potential. And this again is due to the interactions, but we still cannot really explain why the pseudo gap happens, okay? But the behavior resembles the cartoon very much. In addition, we look at the magnetic order in this region that we call B, because we observe blocks. Okay, so we found that nearest neighbors spins are aligned ferromagnetically, and they form blocks antiferromagnetically aligned with each other. So this is like the 1D version of what Murigal et al. Observed experimentally in the lather material. So basically, this behavior arises from the localized spins, the spins of the electrons that are in the mod split orbital. So something that we think or we propose is that maybe the block state observed by Murigal et al. Could be a manifestation of an orbital selective mod phase. Experimentally, we still don't know. Okay, so let's, the next thing that we decided to do is then to focus on this phase and try to study what is going on in it in more detail. So we simplify things even a little bit more, okay? And we decided to go from the 3-orbital model to an effective 2-orbital model. Okay, so this is what we did. We, in the orbital selective mod phase, we have the mod orbital that has a localized spin, has population 1. And the other 2 orbitals had population 1.5, as I showed you in the previous figure. So we said, okay, we are going to go from 3 to 2 orbitals in this particular phase by writing a 2-orbital model with 2 orbitals and with a doping of 2.5, okay? Because we think that this is the picture regarding distribution of electrons that will capture this behavior. Okay, so we did that and we studied the static structure factor, okay? So in the limit in which we have 2 electrons per side, okay, so this is going to be a little bit actually below the 2.5 that would correspond to the parent, we have an effective spin 1, and we find that it orders antiferromagnetically, so there is a peak at pi. But now we start adding electrons, and what we find is that the peak moves away from pi, so incommensurability develops, and we start observing in the localized spins these behaviors. You see, for example, at 2.5, which would be the parent compound, we get the peak at pi over 2, and we get the size 2 blocks. But as we add more electrons at 2.66, for example, we get these 3 spin block structures. And at 275, we get 4 spin structures, okay, spin blocks. So when we come back to n equals 3, now we have an integer number of electrons per side. Now we get effective spins 1/2 that again order antiferromagnetically, so we get again the peak at pi. So this is a very interesting behavior that occurs in this orbital selective mod phase. In addition, we look at so this was in the chain, okay? But I said that we would be comparing with what happens in the ladders. This is numerically much harder. But we did calculations in the ladder and we found a similar behavior. So we start with the peak at pi, but then incommensurability develops. And as you see, we go from the pi 0 situation to the blocks, okay? So here we see the blocks observed experimentally in barium iron selenide, and then we go to these more complex phases with blocks of size 3. So there seems to be a lot of variations, okay? So in order to do better, we had introduced even an additional simplification, okay? So you can see here that the lines correspond to the result for the two-orbital model that I just described. And then we have all these points that are in very good agreement with the lines, that corresponds, that I label Kondo. This is an effective Kondo model that we constructed just to study the multi-orbital Hubbard model in the orbital selective mode phase. Okay, so this is the idea. The charge degrees of freedom are frozen in the localized orbital, so we introduce localized spins. That leads us to a model that has an itinerant orbital. Okay, this is the original itinerant orbital. Then we have the Coulomb interaction in that same orbital. And then we have a Heisenberg term between the localized spins, and this is how the Heisenberg coupling is related to the hopping in the mode orbital of the two orbital model and the Coulomb repulsion U. And then we have a Kondo coupling between the localized and the itinerant spins. Okay, and this is the relationship between the Kondo coupling and the original Hund coupling. And now, in order to see what happens with the doping, okay? So this was the two-orbital model for the parent compound. We have one electron in the mode-insulating orbital and 1.5 in the metallic orbital. So in order to go to the Kondo model, we say, okay, we have the localized spin here, and we have to put 1.5 electrons in the metallic orbital, okay? And due to the particle-Hall symmetry of the Kondo model, this is going to be equivalent also, the same result we will obtain if we put 0.5 electron in the metallic orbital, okay? So this is basically the relationship between NK and NH. This is Kondo, this is the two-orbital Hubbard, okay, or that. In order to show you how well this model works, here are A of k omega calculations that we made, okay? So this is with the two-orbital model in the region where the Kondo model is not a good approximation, because here the two orbitals are metallic, okay? So you see the Fermi energy here, and here is the density of states. Both orbitals are metallic. But then we go from U over W 0.1 to U over W equal 1. And here, with the two-orbital model at 2.5 doping, okay, we see how one of the orbitals becomes a mode insulator, splits in two, is the red spectral weight here, while the other remains metallic, okay, and determines a Fermi surface. And these are the equivalent results that we obtain with the Kondo model in this situation, okay? So you see how we capture very well the behavior of the metallic orbital. In addition, notice that this is very different to a free particle, okay? Okay, so yeah, I forgot to say that. This was the paramagnetic case, and this is the block magnetic situation. So here, this is superimposing the metallic part of this model with the result for the Kondo model, and you see the excellent agreement that we obtain between the two models. So because of this, we have been using the Kondo model to explore a lot of the properties of the orbital selective mode phase. So we decided to look at the phase diagram as a function of electron filling and as a function of the Hubbard repulsion, keeping the J-Hund equal to 1/4 of U. So what we see is that this is the situation in which we have one electron in the so that would be 1 electron in the metallic orbital, so 2 electrons in total, and this corresponds to 2 electrons in the metallic orbital, 3 electrons in total. Okay, so we see that there is at low U, for all dopings we have a paramagnet. As U increases, we get a Mott insulator at both integer fillings, okay, which is this peaking pi that I already showed you in S of Q. But as we start doping, and U is relatively large, we go from the antiferromagnetic state to the block states. And you see we have blocks, but depending on the filling, as I showed you before, we have blocks of different size. In addition to that, we found a novel phase, which is this block spiral phase. Oops. This a block spiral phase, okay? So this is a very intriguing phase. Notice the following. In a regular spiral, we have spins that are tilted with respect to each other, okay? What we are finding here is that we have blocks of 2 spins ferromagnetically aligned that are tilted with respect to each other. And as we increase the doping, we found regions also with blocks of 3 spins that are tilted with respect to each other. So this is a spiral phase that appears in this multi-orbital Hubbard model without having Zaloshinsky-Moreo interactions or without having put frustration by hand. So there seems to be a hidden frustration that appears due to the competition between the Coulomb repulsion and the Hund coupling. So this is a phase that so far hasn't been observed, but we believe that it could exist in some materials. The problem is that we cannot predict what materials may have it. So this is something that probably experimentalists will have to try to eventually do, okay? So using the Kondo model that I just mentioned, we also look at what A of k omega is doing in the block spiral phase. Okay, so these are results in the 2-orbital Hubbard model. These are results, the corresponding results in the Kondo model. So this is when we have the block phase, okay, so you see we have basically the metal in both models, and this is when we have the spiral block phase. And you see that now we get 2 quasi-particles, okay, that are degenerate only at the center and at the boundary of the Brillouin zone. And these 2 quasi-particles correspond to the 2 possible chiralities of the spirals, okay? The spirals can go in one direction or in the opposite direction, and these states appear here in the 2-orbital Hubbard model, and also they appear very clearly in the Kondo Heisenberg model, okay? So this is a very interesting development. Again, this occurs without putting terms that explicitly produce this kind of thing. And because of this behavior, this is common, for example, in systems with a spin-orbit coupling, for example, or things like that. In many topological models, there is a chance, and we haven't explored it, that there may be some hidden topology in this phase that could be explored. Okay, so let's see what other properties experimentalists have found in the ladder compounds in barium iron selenide. So in addition to the block spin order, they found, they studied S of Q omega, and they found an acoustic spin mode with a bandwidth of 50 millielectron volts, and 3 optical modes, 2 at about 100 millielectron volts, and 1 at 200. So our next calculation was to try to calculate S of Q omega, okay, which is not a simple task at all. Okay, so we work with the 3-orbital model using DMRG in chains. So we work in this with the parameters that gave us these size 2 blocks, and we calculated S of Q omega. And this is what we obtained. Okay, we found an acoustic mode that has a bandwidth of 50 MeV, and an optical mode at about 100, okay? So this is in very nice agreement with what the experimentalists found. In addition, it is interesting to see that this mode, the acoustic mode, has a maximum at pi/2 and disperses in this direction, but there doesn't seem to be a lot of spectral weight for the higher momenta in the Brillouin zone. We believe that this is due to the fact that this comes from magnetic excitations between the blocks. You see that when we have size 2 blocks, this effectively makes the lattice size increase, become double of what it was, okay? Instead of being A, now it becomes 2A. And when the lattice size increases by 2, the Brillouin zone size decreases by half, okay? So you see that instead of having the most of the weight here, we have it at pi/2. So this could be an indication, again, of these blocks talking long range with each other. On the other hand, the optical mode is something that occurs at high values of the momentum, and it seems, I will show you later, it seems to be related, or this the value of omega of its position seems to be correlated to the Hund coupling. So we believe that this mode arises from a spin flip within the same block. Okay, and so this is why the mode doesn't disperse a lot. So notice that this is a very difficult calculation, because for each value of the 200 frequencies that we use, we had to do a DMRG calculation. Okay, so let's see what happens with S of Q omega as we go to larger blocks, okay? So these are the results that I already showed you with size 2 blocks. These are results in the regions with size 3 blocks. What you see is that this is again in agreement with the fact that the acoustic mode comes from long-range magnetic interactions between the magnetic blocks, because now the lattice size is 3 times what it was, the Brillouin zone gets reduced by 1/3, and here is where we see in the lowest 1/3, we see the strongest spectral weight. And in addition, we also see the optical mode. We also did the calculations in a ladder to see that this wasn't something that only happened in the chains. So in the ladder is a much higher effort. We did it with a magnetic structure observed in the experiments for barium iron selenide, and we found exactly the same behavior, okay? So the acoustic mode and the optical mode for Qy equal to 0. For Qy equal to pi, because now this is a ladder, we found that there is a spectral weight, but much smaller, okay? And so most of these contributions seem to come from Qy equal to 0. So let's look a little bit more about S of Q omega and see how it depends on U. Okay, so we fix J Hund over U equal to 1/4. This is for parameters with the size 2 blocks. And the interesting thing is to see that this is the part where the Kondo model doesn't really capture the Hubbard, okay? But the maximum weight is at pi. But as the blocks start forming, we start seeing a spectral weight at pi/2. Then when the blocks are more formed, this spectral weight is more intense here. And once the blocks really form, we get the optical mode, and this spectral weight becomes much more negligible. Eventually, as U continues to increase, because this is kept constant, J Hund also increases, and you see how the optical mode goes up, okay? While the amplitude of the acoustic mode goes down. This could be related to the fact that the acoustic mode is ruled by an effective J that should go like 1 over U, okay? And also we see that for large J Hund, this optical mode starts developing a small dispersion. So now let's see what happens as a function of J. Is kind of similar. So we work now at U over W equal to 1. And again, we see that eventually when we get to J, that so that the blocks start stabilizing, we get a lot of spectral weight at pi over 2. It becomes more intense. Eventually the blocks form and we get the optical mode. And as J Hund continues to increase, now the optical mode gets separated and increases more with J. Okay, so here this is kind of evidence that how J Hund controls the position of the optical band. So as a result, in the orbital selective mode phase, when we have the blocks, we haven't studied this for the spirals, we found that an acoustic dispersive spin wave mode develops from antiferromagnetic correlations among the ferromagnetic blocks. The spin wave bandwidth establishes a new energy scale that is strongly dependent on the size of the magnetic island and becomes abnormally small for large clusters. Okay, you see here we have the 4 size clusters and this amplitude gets reduced. And the optical, mostly dispersionless spin excitation modes are present for all blocks states, and we believe that they come from on-site spin flips. Okay, so now I'm going to change subjects and I'm going to address the second question, okay? So whether padding could develop in these, in multi-orbital iron ladders. So we know that it happens in the cuprates. There are compounds that have a ladder structure of copper, of copper oxygen. These materials become superconductors with pressure, and Elvio and Rice studied a long time ago that in ladders there is a tendency to padding in ladders with single orbital models, okay? So now we are going to look at what happens in two orbital ladders, okay? So these are DMRG studies. So this is basically to show that the magnetic order with order pi 0 develops, but not for all values of U over W, okay? So this again is ruling out the weak coupling approach. It develops at intermediate values of U, okay? And then the question is, we know that superconductivity occurs with pressure, but in fact, DFT calculations by Zhang and Lin et al. Demonstrated that effectively pressure induces doping in barium iron selenide, okay, iron doping. So we decided to study padding in this system by looking at the difference in energy between putting two electrons together versus putting two electrons separately. So basically with DMRG, we calculate the ground state energy with for the parent compound, and then we calculate the ground state energy for the n-1 particles and the ground state energy for n-2 particles, and we construct this difference in energy. And when this is negative, it means that it's energetically more favorable to put the two particles together rather than separately. And that would indicate pairing. And what we find is that the pairing is observed, but not for all values of U. It happens only at the intermediate, in the intermediate range. This corresponds to the orbital, to the orbital selective mode phase. Okay, so it's very interesting to see that neither in weak coupling nor in strong coupling, this pairing occurs. Again, the pairing occurs despite the fact that there is no explicit Hall attraction in the Hamiltonian. Okay, so these results were in the ladder with two orbitals. So now we decided to look at chains in order to be able to go to larger systems, okay? So these are results for two orbitals in a chain. And again, we observe that in the chain, there is pairing at intermediate values of U. So at large values of U is not, I mean, it's even worse than in the ladder, the pairing here. So how do the holes arrange in the ladder? And we found that it's very interesting to notice that what happens is that the holes arrange in a way that they try to disturb the least possible the magnetic order. So this is actually not a real ladder, okay? This is a chain where here what I'm plotting are the two orbitals in the same site, okay? So this is one site, these are the two orbitals. And here you see that the red lines indicate spins that are ferromagnetically aligned, and the blue lines indicate spins that are antiferromagnetically aligned, okay? So these are ferromagnetically aligned because of the Hund, okay? And this is the antiferromagnetic order that results because of the U. What we notice is that the holes, first of all, they are in different sides of the chain because of the Coulomb repulsion. But they also because of the Coulomb repulsion. Also notice that they go into sides that I mean there is a pi shift across the hole. Okay, so usually if this were replacing the electron that was originally here with a spin down, this guy would have to have a spin up, okay? But the presence of the hole causes a pi shift. The other hole goes into the next nearest neighbor side, but in the other orbital, and there is also a pi shift. So it seems as if in order to introduce the holes, is as if we just imagine that this is like a rubber band, so we move this guy to here, and in the middle we put the holes so that it doesn't disturb the magnetic background. And you can see that if this guy were to jump, this is going to come here, and again the magnetic background would not be disturbed. So it could be, maybe it could be possible that the magnetism plays a role in this tendency that we observe towards pairing. So then last question I will address is whether the pairs can condense. And what we found is that we look at two types of pairing operators. So this one, that is the nearest neighbors interorbital singlet pairing operator, and the corresponding one with a plus sign here, that would be a triplet. So we calculated the pairing correlation functions as a function of distance, and we found that the singlet decays more slowly than the triplet, and the rate of decay for the singlet is kind of similar to rate of decay for orders that are enhanced in one dimension. Okay, so we think that this could be some evidence that there is a tendency to pairing in multi-orbital Hubbard models in regions in which the relationship between U and J is the right one. Okay, so it doesn't happen for all values of the parameters. Okay, so let me summarize my talk. The message to experimentalists would be that studying 3D, 4D, and 5D materials with chains or ladders is interesting because a good comparison with theory is possible. To crystal growers, I would like to say that a search for appropriate candidates to realize the block states is important. There are some iron materials that seem to have some of the blocks, but there may be many more. And to neutron scatterers, it is important to confirm the exotic dynamical magnetic properties unveiled by our work. The magnetic blocks are usually caused by dimerization or frustration terms added to the Hamiltonian, but here they arise from non-trivial electronic correlations that develop in the orbital selective mode phase. This is basically the message. We find the orbital selective mode phases that develop magnetic block structures and magnetic spiral structures with a very peculiar S of Q omega spectrum. And finally, these models also seem to have a tendency towards producing pairing, and this could be good indication of that these are the necessary ingredients to produce superconductivity in the iron-based materials. Thank you.
Thank you very much, Adriana, for this very interesting results. So we have time for questions now. Feel free to unmute yourselves. Let me see. Well, yes, everyone to unmute. Maybe I wouldn't say a question, maybe a comment. Now with the community of cold atoms and optical lattices being able to produce ladders, maybe looking at these results that you just showed to us is a new, let's say that they have a new platform to observe essentially what you have just showed us.
Yeah, I think that it could be possible. That what I don't know if they can work with multi-orbitals. I think that they are basically particularly with Hubbard interactions at the very beginning, with just trying to reproduce the physics of the single orbital. But in principle, as they get better, it is possible that they could do that.
More questions?
I have a question.
Yeah, hi.
Hello, Adriana. I'm Karen Horberg from Argentina. Thank you for your very nice talk. Adriana, I was wondering about your pairing correlations because you showed the pairing correlations of, the pairing this predisposition with the energy difference, okay, for two holes from the half-filled case. Yes. So you find a tendency to pairing with the holes in this last figure we see here in your summary. But then the pairing correlation you measured is a pairing correlation of creating two particles, so it would be not holes but electrons. Am I understanding this correctly?
No, this let's see. Is delta dagger. I think that let me see how I let me see.
Okay. Then
it's so it will be. Yeah,
you showed the operator with the electrons, but so it's holes. So then my second part of the question is, you have a tendency to pairing from the half-filled case, so a very slightly doped case, and then you would expect this doping to the tendency to pairing to continue for a larger doped system. Is this so?
We would expect, yeah, we would expect that. Yeah, but it's harder to explore, and particularly in small systems, it's not so simple to explore. But yeah, so that is the idea. Yeah.
Okay, thank you, Adriana.
Mm-hmm.
Other questions? Let's go.
Okay.
So maybe one short comment, Adriana, since nobody else is asking. Some years ago, we calculated here with a group in Bariloche. We also calculated for the condo lattice system. So we had a similar model to the one you did, and we also found these magnetic orderings. I can send you by email the results.
Yeah.
We also look at the spin structure factor, and we see these two or three ordering you were mentioning for a very similar model. So it's and just in case, I mean, it's similar.
I think that I look at your papers, Karen, and I think that we reference your work in our work. I think.
No, it's okay, but it's interesting that these patterns arise in similar models, and I mean they seem to be quite ubiquitous in different models. So this is
so I think that exactly that I think I don't remember the details. I remember seeing your work. I remember that it wasn't exactly. There was some difference in the parameters that we are exploring, but yeah, we believe. I mean, because we were focusing on a particular range because we wanted to make the comparison with the nictiles. But yeah, I remember that you also saw the blocks, and again, this could be a phenomenon that is much more generalized than that everybody knows, and this is why probably experimentalists need to start looking at that, because it's emerging in many other things. The thing is that neutron scatterers need to know what to look for, and many times if you don't look for something, you don't see it.
Exactly. Yes. Well, let's hope they find it experimentally. I'm looking forward to that.
Thank you, Karen. Well, I don't see any other questions. So let's thank Adriana again. Thank you very much for being with us today, and hope to see you all next week.
Okay. Thank you.
Bye.
Bye.
Thank you. Goodbye.